In this video, I'm going to talk about transistor, okay, also called BJT. BJT is nothing but bipolar junction transistor. BJT is a basic electronic semiconductor device with the three terminals. It has a three terminals. The three terminals are base, collector, and emitter. And it's a three layers, Npn. All three layers are not same, not equal. And the doping ratios are also a little bit different. So we call this as, since we have three layers, N and P and N, we call this as Npn transistor. Another one is PNP transistor. Okay, here also collector, base, emitter. Okay, this is symbol, you can see it, Npn transistor and PNP transistor. So basically for Npn transistor, the difference between Npn and PNP is the arrow. If the arrow is going out, the arrow is always indicated on the emitter. Okay, so if arrow is going out, that's Npn transistor. If arrow is going in, that's a PNP transistor. So here the current IE equal to IC plus IB. IB is really very small, okay, in microamperes. So IB is very small. Most of the cases IE equal to IC, but we're not going to take IE equal to IC in this video or in this chapter. Okay, so the doping concentration in collector, base, emitter may be, so as I mentioned, the doping concentration is varies. Okay, so the behavior of the device is not electrically symmetric. That means, so if I take this Npn transistor, I cannot use this terminal emitter as a collector. Okay, it's not a symmetrical device, so you cannot interchange the ends. That's what it meant. Now so I think further I'm going to talk about only Npn transistor. Okay, so here base collector junction and base emitter junction. Okay, so here is the base is connected to P. I'm going to mostly talk about Npn transistor. So this VCB, the external voltage we supply between C and B, must be higher than VB. VB is going to be most probably around 0.7 volts. So that way this junction is going to be forward biased. This transistor is going to be operated in three ways. So for example, if you have Npn transistor, okay, now if these two junctions are forward biased, then act like a closed switch. Okay, and if these two junctions are open, then reverse biased, if these two junctions are reverse biased, it will act like an open switch. So if these two junctions are forward biased, act like a closed switch. If these two are reverse biased, act like a open switch. The third one is the base emitter junction is forward biased and base collector junction is reverse biased, then it will act like an amplifier. It amplifies the signal. Most of the cases they're going to use the transistor to amplify, but in our power electronics we're going to use it as a switch. So most probably we're going to use it either both junctions are forward biased or both junctions are going to be reverse biased. Now to get the values, IC is the collector current, IB is the base current. The relation between IC and IB equal to, or IC or beta equal to IC over IB, where beta is the common emitter current gain. That value is given by the manufacturer. Most of the cases that value is between 50 and 200. Some transistors might have around 1000. Okay, so if beta value, now the next term I'm going to define is alpha. Alpha is called common base current gain. That will give a relation between IC and IE. As I mentioned, IC and IE are very close because IB is very small. So alpha value is approximately equal to 1, close to 1. Okay, here alpha will end up with 0.99 if I take beta value as 100. So the transistor is going to be operated in mostly three modes, but I saw the fourth mode here. I'll talk about three modes. So active mode, when one junction is forward biased, another junction is reverse biased, that's active mode. Cutoff mode is both junctions are reverse biased. Saturation mode is both junctions are forward biased. Okay, so this is the VI characteristics of transistor. I don't think we need to go too deep into the VI characteristics of transistor as long as you understand the basics, and I'm pretty much sure this is already covered in power electronics. Sorry, this is already covered in basic electronics. Now, so when the active mode of operation, what is the voltage range? So if it is active mode, VA must be less than VB, must be less than VB, must be less than VC. Okay, if VB is higher than VE and VC, that's saturation mode. So active mode, it amplifies the signal. Saturation mode acts like a closed switch. Cutoff mode acts like an open switch. Okay, if VE is greater than VB and VB is greater than VC, that's a reverse active mode. Usually we don't operate the transistor in this mode. We operate the transistor in these three modes. Now the next transistor is MOSFET. MOSFET is nothing but metal oxide semiconductor field effect transistor. So this transistor works on the works based on the electric field. Okay, so that's the reason field effect transistor. They use a metal to make this transistor. So metal oxide semiconductor field effect transistor, that's called MOSFET. Okay, compared to BJTs, MOSFETs are small and consumes less power, and manufacturing process is relatively simple. So that's the reason MOSFETs are famous. Enhancement type MOSFETs are more common transistors. This transistor conducting channel is lightly doped and normally off without gate voltage. So let me talk about that here. So here also there are two types of MOSFETs. One is N-channel MOSFET, another one is P-channel MOSFET. So you see there are four terminals. One is body, or also called substrate terminal, source, gate, and drain. Most of the cases, this drain and body are going to be connected together, so we call this as a three-terminal device. Okay, so this is, as I mentioned, N-channel MOSFET. So here is a N-type material. N-type material, the remaining everything is P-type material. Now here we keep a oxide. Okay, this highlighted place is oxide. Thickness is very small. The TOX is 1 to 10 nanometer. The thickness here, this blue area, is 1 to 10 nanometer. Now typically length of this is 0.03 micrometers to 1 micrometer. So I'm taking this as a length. Okay, and it's a two-dimensional. We cannot see width, but width is like this. The width is 0.1 micrometers to 100 micrometer. Okay, so as I mentioned, even though it is a four-terminal device, source, drain, gate, and body, most cases body and source terminals are connected together. My apology, I said drain and source in the previous, but body and source terminals connected together to ground. So we call this as a three-terminal device. Another name for the MOSFET is insulated gate field effect transistor. Okay, so here is the oxide and this is a metal part. Okay, so whenever we give power supply to the gate, okay, a positive supply to the gate, the metal there, I'm talking about this metal is going to act like a positive, so this is going to be positively charged. Okay, now what is the p-type material is going to have? Majority carriers are holes, so this p-type material is carrying lots of holes. At the same time, minority carriers are electrons. Okay, it will have some electrons. So whenever I give positive terminal there, automatically it attracts all the negative charge carriers up here. So the minority carriers are going to be here. So whenever we create all the negative charges here, a channel is going to be created. So here this is already N-type material. There are lots of free electrons. Majority carriers of electrons, minority carriers are holes. Majority carriers electrons, minority carriers are holes. Okay, so whenever we so the channel is going to created. So whenever we supply voltage from drain to source, the current is going to pass from drain to source. Okay, another important thing here, the field is going to be created since we have a positive charge and negative charge. Whenever we separate positive and negative charges, there is always electric field between these charges. So the gate current passing through this gate is 0 always. So that's one of the important point in the MOSFET. Gate current is always 0. Most of the cases approximately 10 to the power minus 15 amperes, but we can neglect that. Drain voltage is always positive with respect to the source. So we always apply higher voltage at the drain, lower voltage at the source. Remember, the body and source are going to be connected together. I think at the starting of this video I mentioned in reverse direction. Okay. MOSFET is a symmetrical device, so drain source can be interchanged without changing the characteristics. So it's a symmetrical device. We can change source to drain, drain to source, not like transistor, regular transistor or bipolar junction transistor. The channel is created by inverting the substrate surface from p-type to n-type. Hence, the induced channel is also called an inversion layer. Okay, so I'll stop this video. So those are the basics about MOSFET as well as the transistor. Okay, so if you have more questions, please ask me in the office hours or during the class time. Thank you.